The physical boundary defining the search area at Gander Lake in Newfoundland is strictly governed by extreme depth and zero visibility. For 79 years, the exact resting place of a Royal Canadian Air Force consolidated B-24 Liberator, known in the records as RCAF Liberator 589, Code D, remained entirely unconfirmed. The primary operational objective in this specific freshwater environment is not physical extraction. The objective is to verify the exact location of the airframe on a deep underwater ledge and establish a structural baseline without disturbing the site in any way. This requires operating in a lake whose depth and optical conditions defeat ordinary search methods. The environment demands absolute adherence to remote sensing protocols before any further evaluation can occur. The heavy bomber entered the water on September 4, 1943. Locating the wreckage required a modern survey team to overcome specific local limitations that had defeated all previous tracking attempts. The target lies in a deep dive range, with survey reports placing the wreck around 38 to 46 meters rather than at one exact depth. Operating at 157 feet in this lake introduces severe logistical and technical constraints for any expedition. The lake water is dark brown from dissolved organic material. That saturation absorbs light and reduces visibility to a narrow working range, reported by divers as roughly 1 to 2 meters even with powerful lamps. A conventional visual search from the surface or the use of ordinary shallow water cameras could not produce a reliable site picture here. The 79-year gap in positively locating the heavy bomber was enforced by this specific combination of depth, darkness, limited visibility, and poor surface search data. In 2022, a technical expedition deployed multibeam sonar to break this historical holding pattern. Environmental masking made multibeam sonar the decisive tool. Multibeam sonar generates a dense acoustic model of the lake floor, bypassing the visual limitations of the tannic water by relying entirely on sound pulses. The survey team systematically painted the underwater topography, carefully logging the returning data. This acoustic mapping successfully fixed the position of the wreck, while the specific identity still had to be evaluated against historical records and later visual evidence. The sonar data confirmed that a large aircraft wreck was lying far below the surface in the expected zone of Gander Lake. Establishing that geographic location in the reported 38 to 46 meter depth range was the mandatory first step before any further technical assessment could proceed. The remaining task was to use that fixed position as the entry point for controlled visual and archaeological confirmation. The multi-beam sonar pass produced definitive location data without physical contact with the airframe. That depth placed any later inspection firmly in technical deep water territory. The successful survey in 2022 provided the first verified geographic position for the wreck since the day it was lost. The resulting data revealed the target in the deep survey zone, but visual and archaeological confirmation still mattered. But how did a massive heavy bomber arrive at this inaccessible depth range in the first place? The immediate 12-day salvage window in 1943 defined the sole physical interaction with the heavy bomber before it was permanently abandoned. 4 crew members were operating the heavy bomber, which relied on the combined thrust of 4 engines to maintain stable flight. Directly after departing the runway, the aircraft suffered an apparent power loss, possibly involving the outboard port engine. That low-altitude failure left almost no aerodynamic margin for recovery. When a multi-engine aircraft loses power on one side during takeoff, the remaining active engines continue to generate forward thrust. Because the aircraft is slow and close to the ground, the crew may have too little airspeed and altitude to counter yaw, roll, and stall. The active engines can push the aircraft toward the failed side, while the wing and control surfaces run out of effective authority. In this case, witnesses reported that the bomber's port wing dropped, that the aircraft rolled several times, and that it struck the surface of the lake. All 4 crew members perished during the initial impact. The massive aluminum structure sank rapidly and came to rest on a steep underwater ledge. The military initiated an immediate salvage operation to retrieve the aircraft and the deceased personnel. A specialized team of hard hat divers deployed to the site, tasked with locating the wreck and bringing it back to the surface. The initial dives successfully confirmed the location of the aircraft precariously balanced on the underwater ledge. The divers managed to recover one body from the wreckage during this early phase of the operation. To execute a full mechanical salvage, the recovery team needed to secure heavy lifting cables to the damaged fuselage. Attaching cables to a massive, unstable wreck in deep, cold, low-visibility water introduced severe handling risks. Contemporary accounts indicate that hard-hat divers attempted to attach cables to the fuselage, and that during the recovery effort, the wreck slipped from its earlier position into deeper water, beyond the practical reach of the divers. Once the wreck slipped deeper, the available diving technology no longer defined a salvage problem, it defined a fatal risk. Standard military hard-hat diving in 1943 depended on surface-supplied air, heavy hoses, and a topside crew controlling the diver's support. At the depths reported for this wreck, the danger was not a simple suit compression failure, but the combined burden of pressure, cold water, poor visibility, surface-supplied logistics, and impaired judgment from breathing compressed air. Those factors made complex rigging on a damaged aircraft extremely hazardous. Chasing the aircraft further down the steep, unstable slope would have forced the divers beyond the practical failure point of their life support system. Military leadership concluded that continuing the lift would likely kill members of the surface-supplied dive team, and the recovery operation was aborted after exactly 12 days. Once the wreck slipped away, the failed cable operation left the bomber to settle deep within the basin. The heavy bomber vanished into the dark water, but how does a modern expedition safely design a systematic search grid for an inverted target hidden on an underwater incline? A steep underwater incline imposes hard limits on remote sensing equipment because acoustic pulses cannot bend around solid rock formations to reveal what is hidden below. The survey team must design an intricate, overlapping search grid to overcome the inherent blind spots generated by the terrain. Relying strictly on remote sensing is mandatory when physical interaction with the site is heavily restricted by non-disturbance protocols. Establishing the initial structural baseline must be accomplished purely through sound. The primary objective for the expedition was to create a reliable acoustic location and a preliminary shape of the target area, not a full forensic map of every scattered component. Achieving this required the survey team to manage the trade-off between mapping speed and data resolution. To detect an aluminum structure resting on an irregular lake bottom, the surface vessel deployed a multibeam sonar array to sweep the bottom. The transducer emitted rapid pulses of sound downward and outward in a wide swath, recording the time it took for the echoes to return. In complex terrain, acoustic shadows and low-resolution returns can hide smaller objects away from the main wreck. To reduce those blind spots, the survey team could not rely on casual surface searching. The surface vessel had to hold controlled track lines and use accurate positioning so that the acoustic returns could be tied to a real location on the lake floor. Every sweep generated digital data that was processed on the surface. The sonar technicians watched for hard acoustic anomalies that broke the natural geological pattern of the muddy lake bed. This acoustic stream then became the route map for later dives. The final data set identified the main wreck site and allowed divers to descend directly onto it, but it did not provide a complete structural map of every displaced part. The resolution was not enough to identify many components away from the main bomber wreck, and later surveys were still needed to map the full site. However, a sonar could only paint an acoustic shape. Data alone could not confirm the specific airframe identity. The geometric orientation of an aircraft upon the lake bed strictly dictates how an inspection team can visually document the coherent hull. The acoustic data confirmed a massive target on the ledge, but positive identification required a physical dive to establish visual proof. The dive team found the aircraft inverted on the slope, a position that controlled how they approached the inspection. The exact rollover sequence cannot be proven from the exterior alone, and the surveyed evidence does not show 4 intact engines still fixed beneath the wings. What the dive team could confirm was the inverted orientation, a damaged forward fuselage, intact wings, a nose wheel extended, and the main landing gear nearly retracted or only partly visible. The visual sequence then moved to the exposed undercarriage. To document the coherent structure, the divers worked in 41-degree Fahrenheit freshwater, where narrow beam artificial lighting was the only practical way to inspect surfaces at close range. Those narrow beams forced a slow, non-contact exterior sweep. The divers could document only one illuminated section at a time. The inspection established an immediate exterior baseline. The nose wheel was extended, while the larger main wheels under the wings were almost fully retracted. This visible configuration helped the team orient themselves around the upside-down aircraft without requiring contact with the fragile airframe. The dive team systematically moved their lighting arrays across the forward fuselage, wing structure, and nearby debris field to locate military features and markings. The narrow beams revealed red propeller warning stripes, RCAF-style markings, a displaced vertical tail fin carrying an RCAF fin flash, and a tail machine gun turret lying near the nose. The presence of these features, combined with the wreck's location, depth, and historical records showing that Liberator 589 was the only Liberator lost in Gander Lake, made the identification highly reliable while leaving the search for unique serial markings as a remaining archaeological goal. The visual sweep satisfied the positive identification requirement and clarified why the 1943 rigging effort had been so dangerous. The aircraft was not an intact lift target, but a badly damaged inverted fuselage in deep, cold, dark water. The proof stopped at the exterior. Strict boundaries prevented any interior access to confirm mechanical causality, creating a hard physical limit on internal evidence. The inverted resting position of the massive airframe, combined with decades of deep sediment accumulation along the ledge, created an absolute proof ceiling. The interior flight deck and all internal crew compartments are completely inaccessible to the dive team. Furthermore, the 4 radial engines were not found in the surveyed main wreck area, and the visible engine mounts showed damage instead of intact power plants. Without engine access or intrusive movement, investigators cannot physically verify the exact internal failure sequence from the wreck as it lies. The remaining evidence had to come from visible exterior material in the forward impact zone, where the dive team identified a critical detached component. The Bombardier bomb release interval control box was discovered hanging freely outside the main structural envelope. The dense metallic unit was no longer secured to any solid airframe mounting bracket, remaining tethered to the wreckage only by a cluster of severely degraded electrical wires. Because this specific component was structurally isolated, authorities granted legal authorization for a tightly bounded single-item extraction. In September 2024, a specialized technical dive team returned to the site to remove it. The extraction plan required a diver to carefully cut the degraded electrical wires using specialized underwater shears. The dive team positioned themselves over the target, acutely aware of the steep ledge gradient falling away directly beneath the nose section. Severing the final wire connection introduced an immediate handling hazard. As soon as the tension was released, the heavy control box dropped heavily and sank directly into the thick layer of sediment resting on the ledge. The impact disturbed decades of fine sediment on the submerged incline, throwing a dense cloud of particulate into the cold freshwater column. The silt out erased visual reference to the artifact and the adjacent hull, neutralizing the diver's lighting and forcing an immediate pivot to blind tactile navigation. If the heavy box tumbled further down the incline, it would pass beyond the safe operational reach of the dive team. The primary diver swept the freezing mud by touch to locate the box before it moved beyond safe reach. The diver maintained buoyancy and hand placement to avoid the hidden primary hull, then located the control box after several minutes and placed it in a recovery bag for the slow transit back to the surface. The artifact left the lake. The main hull remained governed by a different boundary. The presence of unrecovered human remains inside the hull permanently classifies the location as a protected war grave. 3 of the original 4 crew members are believed likely to remain within the wreck, because only squadron leader Grant Mackenzie was recovered in 1943. This verified historical reality imposes a hard ethical and legal limit on all future physical interactions with the wreckage. Large-scale salvage or intrusive dismantling would require formal authorization across legal, archaeological, ethical, and Department of National Defense channels. Management now prioritizes site preservation over physical recovery. Because human remains are believed to remain within the flooded military structure, the governing framework restricts interior penetration, alteration of structural load paths, and any physical interaction beyond remote visual documentation or tightly regulated exterior artifact recovery. After the control box was recovered, the intervention shifted from dive operation to conservation. The isolated mechanical component was transferred to Memorial University's Archaeological Conservation Lab for cleaning and preservation, with public display planned through the North Atlantic Aviation Museum. Exposing deep water artifacts to the surface environment can accelerate material degradation, requiring careful stabilization in a controlled laboratory setting. Once stabilized, the component can support public display and material study without disturbing the protected main wreck. Meanwhile, the massive main hull remains secured in its deep freshwater environment. Recent acoustic and visual data now form the reference record for the wreckage. Leaving the aircraft in place relies on the current stability of the lake environment as part of the preservation strategy. The wreck appears to be well preserved, with limited aluminum corrosion, little or no biological growth, and slow sediment deposition observed during the surveys. Those conditions reduce the immediate case for large-scale physical intervention, while still requiring future observations to be compared against the original survey baseline. Establishing this digital and visual baseline allows site managers to compare future approved surveys against the initial 2022 dataset. Future approved work can use acoustic mapping and controlled visual sweeps to measure degradation, sediment accumulation, and displaced parts beyond the main wreck area. Within the area surveyed so far, the wreck was not judged to be at risk of sliding into deeper water, so future monitoring should focus on condition, preservation, and site security rather than an assumed migration down the lake slope. Together, the identification and the single artifact recovery show the present limit of the site. Definitive historical proof can be produced, but the Liberator remains a protected archaeological war grave under controlled stewardship.